All right, so today we're going to start with a topic that is related to what we're covering so far in the class, but it's a little bit unrelated to fatigue, which was the last topic that we were covering. So we're going to talk about screws and fasteners and power screws and the design of basically non-permanent joints. So in this figure, we're just looking at the terminology of the screw threads. You see things like the pitch, which is like the distance between the thread forms, or like the top of the threads in a screw. You have the major diameter D, which would be this right here, and a minor diameter, which would be the smallest one. And then we talk about pitch diameter, and we're going to use that term for other things like when we're talking about gears too. So that's going to be important later too. And what is not shown here, but it is important as well, is the lead, what we refer to as the lead L. So the lead means the distance a nut around this screw would advance for a full turn. So let's assume, I'm gonna draw this so that you can picture it, but let's assume that this first thread goes in the back, something like this, and gets around it, and then you see this next thread. So usually if let's say, I'm gonna use a different color. If I have a thread and it just goes behind it to the next thread, right? And all you see is that there's just one single threaded screw like this. You would see that the lead, which is the distance that the nut would move in the axial direction of the nut of the screw, would be equal to a pitch, right? But not necessarily. So the first one that I drew here, where in green, where you assume that the thread in the back just goes all the way here, and then you see it on a second thread. So basically this is just a double threaded screw. You would see that the lead is the distance. It would be in that case equal to 2p. So again, just this is the distance a nut would advances per turn. Okay, so that is going to be important. All right, and so not all the screws are the same. They do not all look like this. There's going to be different profiles and different like the shapes of the thread itself. So we can have things like squared threads, where basically you would see something like this for the threads, that the pitch would still be the distance between the one thread and the other. So basically in this case this would be P, and since that's P and these are squares, this would be P over 2, like this distance from here to here, and the same for this, P over 2. Okay, basically making it a square. There can be trapezoidal, so these are square threads. It can be trapezoidal, so in the shape of a trapezoid. One very specific, or like one subcategory of trapezoidals, are the Acme thread. And the only thing important about the Acme is that it's very well defined. So you have values for the angle itself. This is usually referred to as 2 beta, but also the distance between here and here would still be P over 2. So we have the pitch. The pitch would still be defined as the distance between this point and this point, so P, distance between the threads. And again, if it's an Acme, this distance would also be P over 2. And we can find different we can find different types of threads. So for example, another very common one is a butt rest thread, which would look something like this. And these are usually used so that the force only goes in one direction. So like you're screwing it in one direction. And again, there's some design angles here and some standards for the different sizes and stuff. And maybe in the real world they look something like this. They're not straight angles there, but that's just because of the manufacturing. So what's important here is to be able to calculate the forces. Oh, and well, we're going to talk about screws just as different kinds of non-permanent joints. But we're going to start with power screws. So these power screws are going to be very similar to one kind of gears that we're going to also talk about later in the course, which are the worm gears. But the difference between those two, mainly, there are other differences, but mainly the power screws are used to transfer large amounts of power with not a lot of cycles and not a lot of repetitions, or like fast speeds. The gears are kind of used for the other, again, not always, but are usually used for the opposite. Not a lot of power transfer, but a lot of cycles and a lot of RPMs. So some common applications of the power screws are lathes, or screws for vices, presses, jacks. Basically something like this, where you have a screw itself, so just like the axis of the screw, and then you can imagine this, and this is a little bit more complicated, and but you can just imagine this as being a nut that by rotating makes this power driven jack to go up or down. So like you can push something up or down, bring a weight up or down. And so to study the stresses and the forces and everything, just to model this situation, we look at the screw from the side. So a side view of the screw itself with the nut. This would look something like this. Okay, something like that. And the nut can be thicker, and this is going to be important later, because depending on how thick the nut is, there's going to be different threads that are withstanding the forces. And so basically what you have is there's a force going up or down. So like, I don't know, the weight of this on this power driven jack, and what you would see is that there's some reaction forces from the nut that are counteracting that force going down. So this would be F over 2 and F over 2, right? Now again, just to analyze the forces itself, we're gonna use one complete revolution of a thread. So when I go from this point all the way around this, going up, and I get to the other side, I basically did a full circle. If I was looking at it from the top, if I start here, I would go around and end up one pitch in this case, but basically in general, when the nut right here rotates 360 degrees, it would have advanced this length. And what we just said before is that I refer to that as the lead. So if I look at this as how much it rose and how much it advanced, kind of like the slope here, I would have an angle lambda, where what we see is that the distance that it advanced was L, or that it rose was L, while it advanced a whole circumference. So this would be pi d, and we refer to that as either the pitch diameter or just the mean diameter, the diameter between the outer one right here and the inner one right here. Okay, so basically from this we can draw our forces. There is a force going down in the vertical negative direction, F. There would be a normal force going perpendicular 90 degrees with respect to the surface, N. There would be a friction force that also has to be overcome because there's going to be friction between the nut and the screw itself, and that could be just modeled as mu n, or I think the book uses lowercase fn for the factor of friction, F. And basically I would have to apply a force that goes in the right direction, so we're going to name that P sub r, if I want this screw to go up. So if this screw needs to go up, I would basically be like, if you think about, I don't know, having a regular screw. It's not the same, but if you have a regular screw and you have your screwdriver, you would be rotating this in that direction so that the nut goes up or it goes down. So if I want it to go up, I would basically be in this situation where PR goes to the right. Okay, and if I want the jack to go down, I would have a force going left. Okay, so basically this is my free body diagram of forces, and PR would be going right to make the jack go up, and left if I wanted to go down. And so from this I can just do a sum of forces in the x and y direction. So for sum of forces in the y direction, I would have a minus F component of this force going down, so that would be Fn minus Fn, and the sine of lambda, and then this component of n going up, and cosine of lambda, and that has to be equal to 0. And the same for sum of forces in x, so I would have PR, P sub r going right, F would not have an x component, n would be minus n sine of lambda, and minus Fn cosine of lambda equal to 0. So basically just these components in the x and the y direction, same for this y and x direction. And since I don't know what the n's are, the normal forces are, I can just solve for n from one of these equations and substitute in the other equation, and what I end up with is being able to solve for PR, which would be equal to F sine of lambda plus F cosine of lambda over cosine of lambda minus F sine of lambda. Okay, that would be R. If I wanted L, which would be basically the force necessary to bring the jack down, I mentioned before, P sub L. If it's not an R but an L, I would just have a minus here and a plus here. Right? Basically, I'm solving for a force that goes in the opposite direction here. Just put like a minus in there. All right. Now what I can do to reorganize this is divide by 1 over cosine of lambda, both in the numerator and the denominator. So this would become a 1, this would become a 1, and then the sines here and here would become a tangent of lambda. But the tangent of lambda, I know, is equal to, tangent of lambda would be equal to opposite L over adjacent pi dm. Okay, so when I do that, PR becomes F L over pi dm plus F the force and then F the friction coefficient over 1 minus FL over pi dm. Okay, and again the signs, these two signs would just change if I was trying to find L PL, P sub L instead of P sub R for going down, right? Now, like I said before, I'm assuming that this is just like a regular screw where I'm just getting my screwdriver and subjecting it to a torque. Okay, this force PR comes from that torque. So basically, this point would be located here or here or here, and to get that torque in terms this torque in terms of PR, it would just be PR times the radius to get T. So PR times radius, force times the distance where that force is located to get my torque. And so I can use that for my equation here. So I was not really interested in PR, I'm interested in the torque. So if I do that transformation here, I would get a T sub R. Again, R and L are going to be slightly different with the different signs. And the radius that I would be using, this radius right here, would just be equal to dm over 2. So the mean radius where this point is located, this point where all the red forces are located, over 2, just to get the radius instead of the diameter. Basically, I would have F dm over 2 and times whatever I had already. So let me organize this a little bit better. So times L pi dm plus F over 1 minus FL pi dm. And like I said before, if I just wanted the TL, not right, but left, going left, basically trying to make the jack go down, I would have a minus here and a plus here. Now this is important because if the lead is too high or the friction is too low, this TL would be either lower negative, or like 0 or negative, which means that the force required to bring the load down is negative or 0. So meaning I don't need to add any extra loads. I don't need to add a torque or force for it to bring the load down. Basically, the lead is big enough so that the friction coefficient can just be overcome by the load itself. So this is only going to be negative here with my minus sign in the numerator when L over pi dm is lower than F. Yeah. Or it can be rewritten as L being lower than pi dm F. So this is one of the things that we check in design so that we know that when we let go, when we're not applying an external torque like this, the load is not just going to go down by itself, that we actually have to apply TL for the load to go down. And just to organize that a little bit more, if we divide by pi d in both sides of the equation, I would just have that F has to be greater than tangent of lambda. So basically this is what we kind of check. If we have the angle lambda, if not, we would just use this previous one that I had boxed. Now to calculate the efficiency of these torques, we would basically compare it to the ideal case where F is equal to 0. The friction coefficient in that case is equal to 0. So basically we would have an ideal torque where F is equal to 0, and that just yields FL over 2 pi, with this equal to 0 and with this equal to 0, right? I'm gonna erase that because I'm probably gonna use that equation later, but this would be the ideal one. And then the efficiency would just be T0 over TR. and that refers to the thread efficiency. Basically comparing it to zero friction. Now these are specific for the squared threads. If we're doing the Acme threads, then we have to include another angle, like the angle that of the threads themselves, and then these equations that I came up with. Oops, sorry. These equations that I'm showing here for TR and TL, depending on which one we're using, would change a little bit with the second of the angle alpha, but we'll talk about that later. For now, this is pretty much enough. And that extra term just comes from the fact that the forces are not perpendicular to, or like parallel to the axis of the screw, but you have to just take into account a component of it. So basically the F in the axial direction would be F over cosine of alpha. So basically, yeah, you would just introduce a 1 over cosine, and that gives you a secant in some situation. Now, besides these torques that I calculated here, we in like actual applications, the screws also have a what we refer to as a collar. So if I just drew a section of the screw before, but basically what you would see in a real screw with the collar would be something like this. Something like this, and then maybe a little bit of the last one. So this collar, the torque, the screw itself just like goes up, but then you have the actual base where you put your load, right? So I have an F over 2 of the load and an F over 2 of the load going down, like here and here. Literally, I would have some loads here. I don't care about that. Some weight. I'm trying to get up with the jack behind and in front. You would see these loads, but basically whatever the weight, the total force that I was describing here before, this F right here or the F right here would be all of that distributed load, but in reality it's half of the load going on the left side, and this side view obviously on the left side and the right side of the collar. So this is what I would call the collar, right? And then I would have my nut. Again, maybe the nut has 3 threads or something like this. This keeps going down, and I would have the F over 2 going up and F over 2 going up. Now, since this is rotating, since either the screw is rotating because the nut is rotating, so making this go up and down, there is going to be friction in this surface and this surface, right? And it's not necessarily the same friction coefficient from before. So we refer to that as the friction coefficient for the collar. Friction coefficient. It can be different, it can be the same, usually different. But for some of the problems that we're going to use, that we're going to solve, we're going to assume that those are the same. And we also have a dimension for the collar. So there will be a diameter for the collar where those forces are acting, and we refer to that as that distance as DC, the diameter of the collar. Now, because this is turning, the screw itself is turning, like I mentioned before, there is going to be friction right there, which is at a distance of dc over 2, this distance from the center to where the force is located, dc over 2 times the force which would be F over 2 for one of them, but I have 2 of those, so basically just F, and times the friction coefficient. So basically the F would be my normal times the friction coefficient would be my friction force. This would be the friction force times the radius. This would be the extra torque because of the collar. So we just refer to that as the collar friction the torque required to overcome the color friction. So this would be F dc FC over 2. And we're going to use that as well. Now, so far these are all just forces, but what we are or torques, in the case of the torques that I just mentioned, what we're interested in is the actual stresses, because that's what we use in design. So we're going to use normal stresses, F over A, and we know that this is a compressive stress because it's trying to bring the load up or down, so it's compressing the screw. We're going to use torques, obviously, and like I've mentioned 1,000 times in class, and we've done this before, for a cylindrical torque, this ends up being 16t over pi d cubed. So I'm assuming all of you are familiar with that, and that this would be the diameter, dr, which is the minor diameter, which is where the stress would be concentrated, diameter here. And there will also be bending. So actually I'm not going to use sub b. I'm going to use, let's just write it, bending. Because when we look at these, when there's a force in this direction, there's going to be a stress concentration, or not stress, well, there is a stress concentration, but the maximum stress will be here from the bending of that thread. So this is almost like a very short cantilever. If I'm looking at it from the side, and I have this force right here, this is going to try to bend like this, right? So there's going to be a maximum tension right there, right? There's going to be bending, but also, and that's why I didn't use sigma sub b, bearing, the bearing stress from like the actual surface area of the thread itself. So this is pretty much written already, the shearing stress due to the torque, and I know the torque, so basically I just need to substitute all those variables to get the tau. Oh, sorry, so there's gonna be, yeah, the bearing stress, yeah, that's fine. And then this F would be from the area, the pi d squared over 4. I just get a 4F over pi d, again r over 2 to the second, and negative. If we're looking at the bearing stress, let's say I only have one right here. Well, this works for both actually. So if I have the force, there's going to be a bending like I explained before, but for the bearing I would have the force divided by the area, which would be the surface area of the thread. So basically a circumference pi d m times p over 2 should be, like we said before, this would be p over 2, the p pitch now divided by 2, same for this if we're doing the squared threads. And again, the knot might just be there should, if the knot has, I don't know, 4 threads, and then it would be in contact with 4 of these threads from the screw itself, right? So this would be an n sub t, which is just the number of threads that it would be affecting. And so well, obviously this is negative as well, and then I would end up with a minus 2f over pi dm n t p. And finally, for bending, I need, well, my my over I. I need to know that the I would be, or I over C. Let's do, so M, let's rewrite this. It's fine. I over Y, this would be M over this to get my bending. Would be the base H squared over 6. So this is just like 112b H cubed, but then the Y would just be H over 2. And I identify that the base is again the circumference, pi d r times the number of threads, and then the H is P over 2. This is H right here. P over 2 squared over 6, which is equal to pi over 24 with the 2 squared dr and tp squared. And I also know that the m is fp over 4, or f halves times p over 2. So f over 2 times p over 2, that distance, that would give me the moment that this little stress element would be feeling. So when I put these together, I over I, which is basically the same thing I just wrote here, you end up with a stress of 6f over pi dr and t and p. So let's put all of these stresses together on a cube element, and we will need a cube element, not just a square element, to see all of the stresses. And we'll go over these values again in just a second, so that we can see both why those are the variables that I used, but also where the stress would be located on this cube element. So I'm gonna give this a little bit of a 3D component to it, and we're gonna call a z axis, z axis and x axis, and a y axis. Okay, and again, this is just gonna be a cube element, so something like this. And you could probably just say, like, since this is cylindrical, like, you could use cylindrical coordinates for this, but we'll just give it an x, z, and y as we usually do, so that's no more confusion. So there's going to be bending from this force right here. That bending, if I looked at the stress element as a square from the side, I would see this, because this would be in tension. This point right here would be in tension. This point right here would be in compression. Okay, so that's a positive sigma x, sigma z. Let's call that. If I'm looking at it from the side, let's look at it from the positive z direction. So this would be a sigma x. Okay, sigma x. And so basically I would have a sigma x right here. I'm gonna use the red to differentiate those two. The sigma x, and then I wouldn't see it, but like at the back, sigma x. Another super simple one would be, due to the compression, there's a force going down, same on the other side, so this sigma f over a would just be sigma x, sigma y, going in the vertical direction, going in. And now we're going to see the torsion. So the first one would be from the torsion that we calculated here, and that would go on the top of this element. So this tiny element, I would not be able to see it because it would be on this face, on the y faces, or like the x component of the faces, on top of that, coming in and out of the face, like in and out of the board. So let me write these down. So I said there's a sigma y from before, right? Going inside, sigma y, and from what I just said, there's going to be a tau coming in this direction. Let's say that this is rotating in that direction, so the stress, or actually in this direction, so that it's consistent with the stress that I just drew. So at the top phase of my stress element in a 2D representation of it, it would be coming towards me. Basically what I'm saying is, if I'm looking at it from the y-x, if I'm looking at the y-x plane, it would be coming the y-x plane, it would be coming towards me, so in the positive z direction. Okay, so basically I would have this tau. And just as a reminder, because some of you have probably forgotten about this, that would be a tau yz, because it's on the y face, the normal face to the y component, and in the z direction. Okay, and then this would be tzy, which is basically the same. And these two have to be the same, going up and coming in towards this location. And then from like the most typical definition of shear, which would just be a force over area, but a shear force, not a like these p's that we actually referred to for the normal stresses. And this would be a T over R to get that force from the torsion itself. So from like the center of my screw in the radial direction, as I move away from the radial direction, I'm going to have a force, a shear force, and the area in that case would be the circumference. So area would be the circumference by dr times however many threads the nut is making contact with the screw, and times this distance, this height right here. So it would be this area that I'm referring to. Okay, so the circumference times p over 2, so that's what I'm missing, p over 2 times the number of threads. Okay, that would give me the actual contact area, and then T over R, which is the radius, would be dr over 2. Okay, so that one, if I reorganize it, the shear would be a minus 4. Well, this is all negative, supposed to like the rotation, 4t over 4 from these two 2's, and then all these terms in the denominator, pi dr squared and tp. Okay, that one would be located, like I mentioned before, from the center of my screw. If I move away, when I'm at this location, at that tiny stress element here, I would see it going outside of the page on these faces, outside here, and then, well, nothing here, or like in and out. So basically what I just said is this would be going in this direction and this direction, and that one I would label it as, for like this one would be on the face of the x, perpendicular to the x direction, and in the direction of the z axis. Okay, and like basically this one would be t z x, but they're the same. Okay, because this tiny element is only deforming, not moving or rotating. Okay, so we're basically done, because I have my tiny cube element, and this, like, the difference here is that this is going to be slightly more complicated than what we've been doing so far. I'm going to list this. Basically what we have is sigma x equal to the bending, right? That's what I said at the beginning. This bending would be the sigma x, so that's going to be a 6f over pi dr and tp. Sigma y from the compression going down, so that's going to be a minus 4f over pi dr squared. A sigma z that is non-existent or 0. A tau xy, which is 0. Again, like if I'm looking at it from the xy plane, there was no, looking at it from the, xy plane here, as the square element, there was no vectors in this direction, so no shear in the typical directions that we usually see. So that's why that is 0. Txy is 0. Then the next one would be t yz or zy, doesn't matter, and this was this term right here, and that is equal to 16t over pi dr cubed, the typical torque, and then the shear from that, the other definition of the shear, so this would be the zx or xz. Zx would also be minus 4t over pi dr squared and t times b. Right? So again, this is slightly more difficult, not difficult, but it's one of the cases that we haven't gone through so much because we usually only have one shearing stress, and it's usually xy. But basically, I'm not going to go over that today. But basically, there would be a von Mises. Actually, we did go over that equation for just a brief moment when I was explaining the von Mises and the distortion energy. But basically, in terms of sigma y, sigma x, sigma z, and then the three different taus, there's an equation for it to calculate the von Mises stress. And to calculate that, it would be 1 over square root of 2 times sigma x minus sigma y squared plus sigma y minus sigma z squared plus sigma z minus sigma x squared plus 6 times tau xy squared plus tau yz squared plus tau zx squared. Move this a little bit more, and that square root of that. Okay, so basically it is very similar to what we've been using, like this square root of 2 can just go inside the square root, so I can make these bigger. And it's similar to when we use the sigma 1, sigma 2, and sigma 3 from the principal stresses after doing Mohr circle, but like I explained in class, there are also equations to just plug in the actual stresses from my cubed or square stress element. So a common problem regarding the power screws or screws in general is being able to calculate this total stress, because that's probably what you would compare to the strength of the material, whatever you're calculating it for. So it could be static loading or fatigue loading like we've done. Probably it's more static loading process, but again, so you would probably just compare it to the yield strength. You don't want the threads of your screw tube to form permanently, or for that matter the ones in the bolt, but they should kind of match. So again, it's not the exact same number, but the process would be pretty similar. So basically what you would have is you would be able to measure the major diameter. So I'm just going to write it with words. You can have information about your major diameter because you can just get you can measure that like literally. So 32 millimeters. You can measure the pitch, so the distance between the threads, one thread and the next, 4 millimeters. And then for all of this, like to actually calculate the correct forces and therefore the correct stresses, you would definitely need the friction coefficients. So those friction coefficients will be given coefficients will be given by the materials that are interfacing, or like the contact between the different materials, and like I mentioned, they could be assumed to be the same. So the friction between the bolt and the nut can be the same as the right here, the collar and the whatever supporting your load, like the stage, basically the one that we refer to as the collar friction coefficient. Okay, so we can assume that they're the same. They're not always the same, but if they're the same material, it's probably the same coefficient. And then a DC, the diameter of the collar. Now you need to know that because that's what's making contact with the stage, whatever I'm trying to bring up or down, and obviously the force, the actual load of whatever you have on top of this, for example, the jack, and you're trying to bring up or down. So that load, you need to know that load, right? So this is the example 8.1 from your book, like the numbers that I'm giving you. So you can see how they solve this, but basically if you know this data, you would be able to calculate things like the thread depth, so all of the dimensional parameters, thread depth, the thread width, the pitch diameter, the minor diameter. You were giving the outer diameter, that's what you would measure. And the lead, so assuming, I don't know, double threads or triple threads. In this case, in that example, they're using double threads. So again, this means, just so that you understand what that means, is from my first drawing here, double threads mean that I would have a thread that goes like this in the front. Let me grab another color. In the front, and then goes back, and then it skips one thread to like make it so that when you put a bolt around this and you give it one turn, it would actually advance 2 threads. Okay, so that's double threaded. There's one thread in yellow, okay, and then another one in blue, for example. So there's 2 distinct threads. So basically every time you move the knot 360 degrees, a full turn, you would advance 2 threads, right? So that's what that means. And you can also therefore calculate everything else that we just went over, which would be the torque. This is the most interesting, or like one of the more interesting ones, the torque required to raise or lower the load. When you're doing the torque required to lower the load, you want to make sure that this is either positive, and that when you're not, actually let's do that one because that's kind of important. So we had an equation for TL, TR, that force going to the right, raising the load, and then TL, which is basically the required torque, and from that force that went towards the left, which is the one required to lower the load. So I have those equations, and for TL I had something like FDM over 2 pi FDM minus L over pi dm plus FL. So of course I need the lead and the minor diameter and all that. But what I want to point out when you look at the book and you go over this example, is that this first part might be negative, 0 or negative, and that's what I mentioned before. If that is 0 or negative, it means that you don't require any torque for it to go down. So basically, if you're not exerting a torque, you're not subjecting the screw to a torque, the load would just come down. And so basically that's what you're going to get. This portion is going to be lower than 0. It's going to be negative. Fortunately, this other term comes from the color. So like the force and the total torque that I needs to overcome not just the load, but the friction that the color is causing to the screw. So let's go back to the color. Yes, I need to overcome all of this friction and all of the forces that we analyzed to come up with that first part of the equation. So everything in green, and that is not going to be enough so that the load that it requires to go down is over 0. So like, meaning if you don't have the force, it'll definitely just go down. But fortunately, there's also a friction. Let's do it, with red here in the color. Okay, And so when you add, let's go back to the equation, green and red together, even though the green was not enough, it's below 0, the total value for this is going to be a positive number. Okay, so basically that just says that if there's no, you actually need to subject it to a torque, to add a torque to lower the load, right? And so these are the questions. We're going through all the dimensional ones, the torque to lower, and then the other questions would be the stresses, all of them separately. So the torsions, the shear stresses, sorry, the normal stresses, the bearing stress, that's going to be also important. And then from these, get a von Mises stress, so that you can, von Mises at the critical stress element, which is the one that we identified, right? So please go over the example of the book, and I'll answer any questions on Friday. This is example 8.1. Now you know where all the equations that they use come from. It's just a basic analysis of the stresses for a von Mises stress, but also them one by one, all of the stresses that the elements are subjected to. And they all come from being able to identify what the forces and the torques are, which is this right here. Okay, so I'll see you on Friday.